Okay, we are recording now.
Did you start the event?
Oh yeah, let's also do that. Start. There. Cool. Okay, so chapter 27. Chapter 27, which is about kin extensions.
Can extensions.
Yeah, so I don't remember anymore, but apparently when we read limits, we had an awkward in this.
Yeah, because we were using a definition in terms of a single functor, right? Between two categories, and that makes things awkward when you're dealing with the the tip of the cone or
Yeah, this
co-cone,
thing.
as the case may be.
Oh, you cannot see my mouse, but it is the one here.
Yeah, and back then, um, instead of trying to create a way to use two source categories, they were like, yeah, let's just use a constant functor. That's sufficient for now. But it
Yeah.
is a little awkward.
Yeah, so apparently that was the awkwardness. Like I said before, I already forgot about that, but I believe that. I believe. Um, so the goal here is to allow a generic description of this thing. So as Manu said, cone and cocone. Um, and let us start by establishing the green category here, where my mouse is, but Marinho can see, as the one category one, I believe, which is the one that contains a single object and a single identity morphism. And what we're trying to establish here, more fundamentally, later we want to replace the category one with an arbitrary category. That's kind of what we want to do. So we have a possible functor k from I to this category, right? And then
Right.
you may want to remember what is I and what is c. So the c is the
I
category in which we are defining the limit for, and the I is the index category that serves as the template for the pattern that would form the basis of our counts. Go on.
Yeah, and the functor D is the diagram functor, which is like it maps out the base of the cone, right?
Yeah. So something else to remember. The whole idea of limits and co-limits and ends and coends is about trying to find the most universal description, in which universal means it cannot be refactored further. Because at some point here we're going to use this refactoring thing that I think we talked about many times in the book anyway. So there's only one possible functor k from I to this category, so the category 1. It maps all objects to the only object in one, and all morphisms to the identity morphism. And any functor f from 1 to c picks a potential apex for a cone. So, and this is the drawing. And I think this is missing a c here on the top right corner of the pink.
Yeah, that category is not labeled for some reason.
Yeah, but this is the category c, right?
It is, yes.
So what is this? What this diagram means? I think that's pretty important. It means that from the index category, we can go to the category C using D, but we're trying to establish a relationship between that and K and F, in which going through F puts us into an apex of this cone here on the right.
Yep.
A cone is an natural transformation epsilon from F after K to D, right? So if you do F after K, there is an arrow going from this composition. Unfortunately, Marinho cannot see my mouse, so he can't understand what I'm talking about. But these two K and F up here to the D down here,
Yep.
that is the natural transformation epsilon, which is on the right here on this drawing. And this drawing below here is actually better. Notice that f after k does exactly the same thing as our original delta c, which was the constant functor.
Yep.
We can now map a universal property that picks the best, right? Which is the refactoring thing. This f will map 1 to the object that is the limit of d in C. And the natural transformation epsilon from f after k to d will provide the corresponding projections. This universal functor is called the right Khan extension of d along k and is denoted by ran kd, which is, I don't know why is, oh, I know why, it's because it's the right Khan extension, so ran.
But there's no k between the r and the n, which is weird.
There's no k between r and the n.
Yeah, it's a Ken extension, but the symbol is ren, which is.
Because of the right, this is the right extension. And that's also the why there's a lan down after.
I would have used rken and lken, but whatever.
Um, cool. Um, let's formulate the universal property. Suppose that we have another cone that is another functor f prime together with natural transformation epsilon prime from f prime after k to d. So this thing. Suppose that we have that. Assuming the existence of that, and assuming that the Khan extension exists, there must be a unique natural transformation sigma from f prime to it, such that epsilon prime factorizes through epsilon. So you can describe one using the best one.
Yep.
Here, sigma after k is the horizontal composition of two natural transformations, one of them being the identity natural transformation on k. This transformation is then vertically composed with epsilon. So what we're saying here is that uh, sigma after k is an horizontal composition, which, as we discussed last week, Marinho, is basically nesting, right? Nesting of functors.
Yeah, to make this diagram a little bit more complete, they could have duplicated the k arrow and put an identity between them, but that would be kind of redundant.
Wait, do you mean between the k on the left and the sigma in the right? On the right?
No, 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 no. They could have duplicated the k, like k from I to 1 could have appeared twice, and then they could have put an identity arrow between the two k's, and that would show the horizontal composition completely. But
I
then
don't
you are
follow. Why?
duplicating k,
Why? Why exactly?
because it says in the paragraph above that this is the horizontal composition of sigma with the identity on k. Well, sigma after k.
Ah, okay. I see. I see. I see. I see. Mhm. What is the other natural transformation? Sigma, right?
It's sigma from f prime to f.
Yeah, this should be I subscript k or something.
No risk
Uh,
of confusion, as
no risk
usual.
of confusion. In components, when acting on an object I in I, we get. Yeah, so this is basically the components. In our case, sigma has only one component corresponding to the single object of 1. So indeed, it is the unique morphism from the apex of the cone defined by f prime to the apex of the universal cone defined by ran kd. The community conditions are exactly the ones required by the definition of a limit. But
But
now it comes the fun part, because now we can replace the category 1 with an arbitrary category A and everything holds. Um, yeah, cool. So the right extension of functor D, which is I to C, which is the base of the cone, along the functor K, which is the vertical thing, I to A, is a functor F, which is doing the diagonal, A to C, together with a natural transformation epsilon, which is F after K going to D. Okay. I have another question. This is a horizontal composition, right?
horizontal. It's a natural transformation f after k. Well, f after k is a functor actually.
Mm-hmm.
Like, there's no horizontal composition of functors, only of natural transformations.
Oh, that's true. This is just normal composition then.
Yep.
It's because I need to remind myself. How do you define compositions of functors exactly? It's been a while since we read that, and I'm just realizing that I need to reread that part.
It's just one after the other. Like it's like vertical composition of natural transformations or normal function composition, sequential.
Okay, such that for any other functor f prime in a natural transformation this, there is a unique natural transformation that goes from the f prime to f. Well, thus the candidate of a better f, but going to the
Actual best.
actual best, um, that factorizes epsilon prime. This is a mouthful, but this is the drawing. I think this drawing is a little bit. It's missing the epsilons in this. There are no epsilons in here. That's okay.
But that's okay. I
Uh,
mean, it would be awkward to fit that epsilon inside of the triangle, right? Because the epsilon is it's about the path from I to A to C. So like it would have to connect to two lines, I guess.
and we already had it here.
Yeah.
Okay. Now some candidates of intuition. So the first thing is that some authors classify the Ken extension as a inverse of a functor multiplication because if you rewrite ran kd as d slash k, this becomes like we are overloading the shit out of these operators. But assuming that you are doing that,
Yeah. Yeah.
this becomes like cancellation.
It kinda sorta makes sense, but I would rather not because no risk of confusion.
I rather like this. I like this one better. The second proposal of intuition. So consider that a functor k embeds the category I inside A, right? Because we have three categories here, and we know that k is a functor from I to A down here.
Yep.
Um, so we are considering a process of embedding, which is a little weird. In the simplest case, I could just be a subcategory of A, and that would make perfect sense in this case. We have a functor D that maps I to C. We have a functor D that maps I to C.
Right.
That is true. That is true.
Yeah,
Can we
that's
extend
the
D to a functor F that is defined on the whole A? So basically what this is saying is that we have a bridge between I and A. It's called K. We have another bridge from I to C. It's called D. Is there a way that we can enhance the capabilities of D, upgrading it to a functor F, because F is actually capable from going from A to C, and A, although it has embedded I inside, it has more stuff, which is gonna matter later on, but it has more stuff. So that's basically the idea, is that we are trying to upgrade a functor. We are trying to make it do more stuff.
Yeah, this is actually a pretty interesting way to generalize a cone, right? A limit of a cone.
Now, I don't follow where the cone in this particular intuition goes
I mean,
plays a
because
role.
because originally we got to here by saying, okay, remember cones, limits, we had that awkward constant functor. Let's use a separate category instead of a right.
Mm-hmm.
And in that case, the second category is trivial, right? It only has one object. But now we're generalizing that to be okay. It can be whatever. It could even
Mm-hmm.
be something bigger than the I that we started from, which is where this intuition comes in, and it's actually pretty interesting.
Yeah, ideally, such an extension will make the composition F after K be isomorphic to D, right? And why that's the case? Because if you do F after K, and you want it to be an upgrade on top of D, it would be nice if that would be an isomorphism with D itself. That would be kind of nice. But it's a little bit of a stretch, of course, because um, there are extra things on A that are not necessarily present on I, and we need to do something about that. So a full-blown isomorphism is too much to ask, and we can do with just half of it, namely a one-way natural transformation epsilon from F after K to D. And then the left K extension that we're going to see later does the other direction on that. And of course, this embedding picture breaks down when the functor K is not an injective, which means that we may be missing some elements on the mapping, right?
Right.
As in the example of the limit, in that case, the gain extension tries its best to extrapolate the loss of information. But as far as my intuition goes, this is now what I think about. Like I know very little about gain extensions, even reading this twice. But I gotta say that a few things. It is related to the whole generalization of limits and ends and co-limits and co-ends. It is now not blocked into a constant functor. It is three arbitrary categories, and it has an embedding process going on. So that's so far what I have. So now we're gonna talking about that. If it's a weaker version of an isomorphism, it's kind of natural, put in this way, to interpret it as an adjunction.
Yeah, because we got adjunctions earlier when we were talking about, okay, sometimes having an isomorphism is hard, but you can have a weaker notion of equivalence that
Yeah,
is still useful, which is an adjunction, right?
yeah. So let's suppose that the right can extension exists for any d and a fixed k. In that case, ren k dash is a functor from the functor category IC to the functor category AC. So now we are handling functor categories. It turns out that this functor is the right adjoint to the precomposition functor, this one. The latter maps functors in AC to the functors IC. This adjunction is this one down here. Uh, so this is the right adjunction, right? This one.
Uh, yeah, it is.
So what is going on? We have a category of functors between these two categories, and this is the home set between f prime after k and d functors. We are saying that this is right adjoint to the category of functors between categories A and C, and the home set between f prime and rank kd. It is just a restatement of the fact that to every natural summation we called epsilon prime correspond a unique natural summation we called sigma. And this is the drawing that we are attempting here. So let's try to understand this. So this is the category on the left of this adjunction up here, IC, and then we have AC on the right, exactly the right of this as well. This is the right adjunction, which means that we are going. I don't remember the right adjunctions. We are going from the right to the left, or the other way around. I think it's right to
No,
the
no,
left.
right is left to right. Like the direction is like if you say right adjunction, that means you are going right. If you say left adjunction, that means you are going left.
Okay, so we are going from D to rank KD in this adjunction here.
Yeah,
Okay, and then we have after F prime after K, we have all the possible morphisms, and that's why we have these many arrows on the left here.
yep.
And the same F prime and rank KD, and we have them in here. Furthermore, if we chose a category I to be the same as C, we can substitute the identity functor IC for D, and then we have this thing. And we can now choose F prime to be the same as rank KIC. In that case, the right hand side contains the identity net transformation. Yes, right, because this is now equal to that. So this is
Yeah,
basically identity. And the left hand side gives us the following net transformation. So the left hand side.
yeah, because you are replacing f prime with the ken extension. Um, over IC, right?
Yeah, no, but you're talking about the left-hand side, so something here is going on.
Well, that's yes, because if you replace f prime in there with rank KIC, it becomes that epsilon down there.
Ah, I see. That's true. This looks very much like the counter of a junction. Yeah, I remember that. Because a junction is basically determined in terms of identity functors, right?
Yeah, it's determined in terms of canceling units and co-units with compositions of functors in a particular order.
Indeed, the right extension of the identity functor along a functor k can be used to calculate the left adjoint. For that, one more condition is necessary. The right can extension must be preserved by the functor k. The preservation of the extension means that if calculate the can extension of the functor precomposed with k, we could get the same result as precomposing the original can extension with k. So this, basically.
Yep.
Notice that the division by k notation, the adjunction can be written as this. So we are swapping this with this notation. And the reason for that is because wait a moment. If what we are saying here is that if you compose k functor with the extension renk with identity, you get back renkk. What does it that even mean though?
It's basically saying, okay, we're going to use k both to go from I to A and also from A to C.
You're gonna use I, you said.
Uh, actually, actually no. Rank KD is this is the base of the thing, right?
Yeah,
So
but we're
actually, this
swapping
is
d with ic. We said that in the beginning. Where is it? Here. We are swapping
yes,
d with identity.
yes swapping D with identity,
Yeah, and
and we
then
get that.
yeah, but then it's saying that there's one more condition necessary. The right can extension must be preserved by the functor k. The preservation of the extension means that if you calculate the can extension for the functor precomposed with k, so this, we should get the same result as precomposing the original can extension with k, which apparently is this.
Uh,
Let me see a thing. Okay, so yeah, I don't know what this means though. I don't know what this means.
if we calculate the can extension of the functor precomposed with k, the functor precomposed with k, we should get the same result as precomposing the original can extension with k.
Hmm.
All right, it's because I see what's going on. The thing that's missing here is that on the right hand side there should have been a dot IC inside of the rank KK. Like it's basically saying if you precompose um, like if you precompose the extension of the original functor with K, that should actually be the same thing as precomposing the functor with K and then taking the right can extension.
So you're saying that after this, they should be composed with IC.
Yeah, it's kind of like, let me actually type this down. It's basically saying, I'm going to type this in pseudo Haskell because, well, I don't have typesetting on Discord, obviously. It's basically saying um, ran um, k IC needs to be equal to ran k um, k dot ic.
Okay, so we are basically saying that if you compose K with a run extension on IC, it's the same as composing it. It's kind of, what's the name of this property? It's kind of like transitivity. No.
No, this is like the naturality condition for like function composition and how it interacts with fmap.
Ah, I know that one. I actually do know
Yeah,
that one.
in the book there's no k after I on the right hand side because, well, k after I is just k, right?
Yeah, yeah.
But this should hold for an arbitrary functor other than I as well, I think. This is like, yeah, see, just before there's that equation, it says, in our case, this condition simplifies to this because, well, k after identity is just k. That's why there's only a k on the right hand of the identity.
Wait, in which equation you're talking about?
Scroll down just a little bit more. That one at the bottom of the page.
This one.
Yeah, because, yeah, if you look at it, it's basically saying, okay, k after the right scan extension over I needs to be equal to the right scan extension over k after I, but
Yeah,
k
no,
after I
it's
is
it,
just
it's
k.
basically the fmap trick that you explained. I'm a little bit not used to this type of can extension thing, so I'm still trying to figure out what this means. But it feels like a neutrality condition indeed. The preservation condition becomes this, which is basically because we are using the division notation for the adjunction, so it can be
Yep.
written as this. And if you, I'm assuming that you are swapping this thing with this,
Yes.
and then you get this thing. The right extension of a functor along itself, k divided by k, is called a condensity monad, which I don't know what that is yet. The adjunction formula is an important result because as we see soon, you calculate can extension using ends and coends. So now the left can extension. So this is basically a mirror of what we just saw.
Yep.
And the arrows are preserved in their direction, by the way, which is kind of weird.
Yeah, like the directions of the arrows of the functors is the same, but the arrows of the natural transformation is inverted.
Ah, so that's why I was confused because this is basically the same thing, but like symmetrical up and down or something.
Yeah, yeah.
So now we are building a cocone using a functor d to form its base and a functor to say the to detect to make the apex. And then we do the same kind of trick as before,
Yeah,
but
see,
this is
that
reversed.
eta, yeah, the eta goes backwards compared to
Yeah,
the epsilon.
epsilon. Epsilon was going from 1 to d in the picture.
Yeah,
And then we write it like this, and this is reversed, as Madden just said, because before it was this going to this, and now it's still the way around. Well, it's the same as before, but just reversing the direction of the natural transformations. Same
it's kind of
diagram as
fun.
before.
It's
Okay.
kind of it's kind of fun how a lot of things in half the things in category theory are the same but backwards of something else.
Well, that is kind of expected in a certain sense. And this is len kd. This is the left adjoint, as we will see later. Um, so the natural transformation is this. It's called the unit of the left scan extension. As before, we can recast a one-to-one correspondence between natural transformations. So this is the same to discover the best. And in terms of adjunction, we get this. The left extension is left adjoint, and the right extension is the right adjoint of the precomposition with k. Just like the right extension of the identity functor could be used to calculate the left adjoint of k, the left can extension of the identity functor turns out to be the right adjoint of k. That's a lot of words. Uh, where did we do this actually? I think we did this.
Yeah,
Are we
here
saying that
we're
this is the left adjoint?
Yes, because it's on the left. We're trying to calculate it by basically plugging in the identity and making
Yeah,
the arrows
and then
all
the
connect.
opposite will happen with the len KD.
Yeah,
We're gonna determine what is on the right of that, which is
yep,
this. And then combine the two results, we get this thing. Um, okay. Um, yeah, this thing is rather complicated. Like this is basically talking about three fun categories, right? Both of them.
yeah, both of them.
Okay.
Is I mean, it's I think it's the same three categories on both sides, but yeah, it's three categories for both of them. It's
Yeah, but
just the
in a
details.
single thing, we're talking about three things in a single thing.
Yeah, yeah, yeah,
The real power of k extensions comes from the fact that they can be calculated using ends. And for simplicity, we're going to restrict our attention to sets, so we're going to talk about home functors a lot.
yep,
And now let's revisit the entire thing with that idea. Suppose that k embeds I inside A. That was the intuition from before. Functor D maps I to C, but C is set in this case. We could
yep,
just say that for any object A in the image of K, that is A equals Ki, and why that's the case? Because we are grabbing an element from capital I category, which is an I, and applying the functor C. So we are basically getting this element
yep,
and calling it A. The extended functor maps A to DI, which is the process of picking an element from capital I category and applying the D functor and going to the set category.
yep.
The problem is what to do with the objects in A that are outside of the image of K. Because if you go up here, here,
Yeah,
K is embedding I into A, but A is, for the sake of the argument, larger than I, which means that there is all of this green stuff here that is outside of the scope of K.
yeah,
Uh, so what do we do about that? The idea is that every such object is potentially connected through lots of morphisms to every object in the image of K. So there is an assumption going on, such that if there is an A prime outside of the visual scope of K, there is a way that you can put that back into the visible scope via morphisms. A functor must preserve these morphisms. The totality of morphisms from an object A to the image of K is characterized by the home functor. So this is the home functor in the category A, going from A to K applied to dash. So something.
yeah. The dash is basically saying, okay, this is an argument to this thing.
Shouldn't be the opposite though? Shouldn't be K dash to A?
K dash to A.
Yeah, because A K dash means getting out of the scope
No,
of
no, no,
K.
no. This is a morphism that takes some A in the big A category and goes to some other object, which is the result of K of the K functor acting on something else.
Oh, you're right. Wait. No, you're right. You're right. You're totally right. I confuse myself between home functor and home set. That's why. Okay. And then you have an F here, which is going from A to C, in this case A to set, and this A here, A prime, is outside of the scope of K, but it goes to set. And this also happens with A, but A is in the scope of K, and it also goes to set. Notice that this home functor is a composition of two functors. So we are saying that this functor that we are saying up there, it's the composition of these two functors, which makes sense,
Yep.
right? And you may ask yourself, why there is no Ka on the on the left hand side of this parenthesis, right? It's because Ka is mapping the element to A, which is already in capital A.
Yeah, the source of K is capital I, not capital A. That would be a type error actually.
Yes. Yes. Actually, what you said is correct. What I said is wrong. What you said is because k can only go from I, right?
Right.
So saying ka will not be possible because a values don't exist in I. The right k extension is the right adjoint of functor composition. So now we are. This is the adjoint thingy. But now instead of C, we're going talking about sets. So this is basically the same as before, but talking about sets. Let's see what happens when we replace f prime with the home functor. So f prime is here. We are replacing it with this composition here. This composition.
We're replacing it with just the home functor actually, and the composition shows up on the left because the home functor, well, f prime is composed with k, and so the identity becomes relevant there.
Ah, that's true. We are just talking about this guy,
Yeah.
the home functor. Okay. So here it is actually. You were right. This is f prime here on the right, and we are just putting the home functor here, and then inline the composition, which means that we are reversing or putting the k inside the parentheses. So there it is. The right hand side can be reduced using the unit dilemma, which basically, well, I don't remember. So you said you reread unit dilemma, Marinho. So why don't you walk us through that?
Uh, okay, so the Oneda lemma, and I was reading this earlier today actually. It's basically it's basically a proof that if you have a morphism that takes another morphism from A to Z or Z to A depending on contravariance, going to f of z, where f is a functor, that's actually isomorphic to an f of a because in the okay, suppose you're taking a to z and going to an f of z that is covariant, right?
Mm-hmm.
Uh, well, in that case, this outer arrow needs to have an f of a inside of it so that it can f map the input arrow over it to get an f of a at the end, right? Oh no,
Mm.
that's actually bad. Yeah, and if it's contravariant, you get the f of z instead. So there are details back in chapter 15. It actually helps a lot if you just type this out in Haskell syntax. It looks kinda
That's fine.
like
I don't remember. We read this chapter a long time ago. I don't remember most of the details. But let's go through how we are transforming this into this. Let's just go through that. I think it's going to be better.
okay,
Uh,
but basically, I'm gonna type this out on the chat. The Yoneda lemma is an identity between those two expressions
so
on
if you
this.
have a morphism between another morphism, a to z, z to a, and f of z, and f should be capital because that's a functor.
Yeah, this is a contravariant. This is a contravariant version. Basically, if you say, okay, if you take a z to an a and you go to an f of z, and assuming the f is contravariant, you must have an f of a inside yourself somewhere for this to make sense.
Okay, but in this case, I don't think we're talking about the contravariant version in here.
Yeah, the covariant version is just flipping the z with the a inside of the argument function there.
Wait, but then this makes perfect sense because these are a bunch of morphisms between a and something else,
Yep.
and this is a functor. Uh, this is a functor. We know that as well. And this is a morphism. So
Yeah, in
the
this
first
case,
condition
yeah, in this,
is already fulfilled. The condition there, and then we are just saying this is equal to f of a. So this is exactly what you wrote. This thing. This.
yep,
Nice. We can now rewrite the set of natural transformations as an end to get this very convenient formula to the right extension. So now we are rewriting this part here in the version of the and syntax,
yep.
which I already forgot about a lot of that as well. That's fine.
Yeah, that's basically the integral sign with the variable on the bottom is basically a for all.
For all i's. Remember that?
Yeah, the home set is basically an arrow, so this essentially translates to, and I have this copied here because I was looking into this earlier. That thing there in typeset thingy is basically this.
Oh, we're gonna see this after. This is in this next chapter.
Yeah,
Well,
yeah, yeah. We
next
will,
session.
we will. Yes.
Anyway, so yeah, here we are. Uh, well, we don't have to go into details of that. I think coends and coends are very confusing, but I accept that this can be done using those things. So this becomes a for all I set of
Yeah, it's a for all I. It takes an arrow from A to Ki, and it is an arrow that takes that and goes to Di.
yeah, this is exactly what you wrote in
Yes,
the chat. Okay.
it is.
There is an analogous formula for the left, which is this thing. To see that this is the case, we show that this is indeed the left adjoint functor to the composition. So now we pick the left adjoint. We substitute our formula on the left hand side. So this thing, it comes from here, this thing. This is a set of natural transformations, so it can be rewritten as an and. Wait a moment. This is a set of natural transformations.
Yeah, because it's in the category uh, of functors from A to set. So the elements of this home set are natural transformations.
Wait a moment. This is a functor, so I accept that part. But this is also needs to be a functor
No,
then.
no, no, no. The entire thing is the like this is a home set, right?
Yes.
It's a home set. But what category are we in? We are in the category of functors from A to set. So the
Yes, that's
morphisms
also
in the
true.
home set are natural transformations between A and set.
Okay, so this is a set of natural transformations. Okay, I see. It can be written as an and, so we change this entire thing to this. Then we can use manipulation of the home functor to replace the coend with an and. I
Yeah,
think we
that's
saw this in the
yeah.
chapter.
It's that identity between a function taking an existential type and a for all polymorphic function,
Yeah,
essentially.
yeah, I remember we discussed about that. Then we can use the product exponential adjunction. So we are grabbing. Yeah, there is
That's
a
just a
product
very
here.
that's just a very fancy way of saying currying.
Yes, because this is a product going. So we have a lot of things on the left of the function, and you're going to this. But instead of doing that, you can just how can I say this?
Instead of taking a pair of values,
Yeah,
you are
yeah,
taking a single value and returning
a function.
a function, which
Yeah,
is an
yeah,
exponential.
exactly. But it's kind of crazy that we both agree on that, don't you think? Isn't it crazy that we understand what you just said looking at this?
Yeah.
Like who would have ever imagined that if we have a like this is a pair. People can't don't see like that, but this is a pair, and we are currying. This is currying. There, the explanation is isomorphic to the corresponding home set. Well, this is also kind of obvious. Sure. Then there's a theorem that we haven't seen yet called the Fubini. How do you say that?
Fubini. I think it's
Fubini.
Fubini. I mean, it sounds Japanese, so I'm going with Fubini, which is how you would
Yeah.
pronounce
So
it
you
in
just
Japanese.
swap those around. The inner represents a set of natural transformations between two functors. The inner end. So this it's telling us this represents a set of natural transformations because uh, this is this is a functor and it's saying that this is also a functor then.
It is.
It is really.
It,
Um,
it actually is. In the type variable of the functor in this case is a, actually.
But why is this a functor? Hmm. Are we just saying because it's set and set is a functor? Is that the argument here?
No. It's because the inner end is a set of natural transformations between two functors. In this case, the functors are the
A,
functors. No. The
the home
functors in
functor.
this case, if you replace the a with a dash, meaning it's an argument, then this home set becomes a home functor on a with the type parameter a. And you can do the same thing on the right hand side, just eliminate the a.
Wait a moment. Are you telling me that if you replace on this current iteration, this is not a functor then?
No, you have to consider this expression all the way out to the inner integration thingy, the for all a, basically.
No, because it's saying that this is a set. So set here, right?
That's not why it's a set, though.
That is not why this is a set, you say.
Yeah, that's if you start from that inner a, it's basically this for all a. Um, this is an arrow where the left hand side is ki to a, and the right hand side is di to f prime a.
Let's see.
And you can define a functor that encapsulates the inputs to this. That is something like type.
Wait a moment. I have a question. Why are you making functions out of these things? Because my understanding is that this is the notation of a home functor.
This is actually the notation of a home set.
Oh, a home set becomes a home functor if you have the dash.
Yeah, because you're basically parameterizing it. You see?
Okay, so this is a home set, and this is also a home set.
Yeah, you can
That okay, so
do.
then what you wrote makes sense. And you have a
Yeah, if you
set of those.
yeah, you just parameterized over the a, and those two home sets become home functors. You see?
Actually, that actually explains to me why they chose this symbol now. Because that's the same thing that we do with integrals, actually. Huh.
Yeah, this is basically interpreting the for all as a type level lambda, essentially.
Huh.
That's a different way to look at it.
So if you put dash here and dash here, this integral removes the subscript.
Yeah, as long as it's
Damn.
actually the same. Yeah, it needs to be the same. No, same variable on both sides, I guess.
Yeah. Yeah, exactly as an integral as well. Damn. Okay. Anyway, okay, so I understand what you're saying there. So this is a set of natural transformations, you say. So K is a functor, I'm assuming, right?
Yeah, k would be a functor. D is a functor. F prime is a functor. But then if you have if you're trying to construct a home set where the output type is a parameter and the input type is fixed to be ki, that itself is also a functor. You see,
Wait, repeat the
that
last
would
part.
be like you can construct a home functor by
Mm-hmm.
saying, okay, this home functor uh, takes a type parameter, which is the output type a,
Mm-hmm.
uh, and its type is an arrow type that goes to a and starts at ki, basically.
Mm. So basically, this needs to be a functor, and this needs to be a functor as well, right?
Yeah, they need to be functors.
Okay, so this is indeed a set of transformations. And then it's basically telling us that you can apply the Ionic dilemma again, which is what you wrote before. So that would be, yeah, this thing. Mm,
Yep.
wait a moment.
That's with the, yeah, you're basically saying, okay, the z in this case, from the upper for all, is the type variable a, and the a, which is what um,
Keeping it.
we're keeping. Actually, I think this is actually easier if I add a little something here. This is basically what I wrote before, except there's an extra thing, and it's kind of similar to what's happening.
Oh, I see.
Actually,
I see. So you are keeping the output from the Z to A. You are keeping that, but you're replacing A with Ki.
yeah, exactly.
I don't know why you're replacing the K with K A with the Ki though.
Because in this case, the K, well, the A in the paper there would be equivalent to the Z in what I wrote in the chat on the
Mhm. Mhm.
for the Yoneda lemma. See, the Z disappears and only the A is left.
Yeah, but we did the opposite of what you said. The A
Because
disappears and the Z was kept.
yeah, but that's because there are two versions of the Yoneda lemma, the covariant and the contravariant. So the direction of the arrow kind of
I see what I see what you're talking about. It's because in the covariant version, the function that you have is an A to a Z instead of a Z
yeah,
to an A. I see.
yeah, the contra yeah, in the yeah,
No,
exactly.
I see. I see. I see. I see. I see. Okay. This is indeed just set of natural summations that forms the right-hand side of the adjunction which we set out to prove. Damn, we have 8 minutes left. Uh, so this is basically saying, uh, yeah, this makes sense to be equivalent to this because this is a home set. This is a home set, right?
This is that's basically yeah, it is a home set,
Yeah.
but it's
But if you want to remove the I in the subscript, you need to remove the I in here.
yeah,
So it becomes D and F after K. Okay, this kind of, that's cool. And then can extensions in Haskell. So all of this, now let's go to the code. And then we have what Manin wrote in the chat before. Uh, let's start with the right extension. So this is the thing that we used before. We replace the end with the universal quantifier and home sets with function types. That makes sense. Look at this definition. It's clear that ran must contain a value of type A, which the function can be applied, and a natural transformation between the two functors k and d. For instance, suppose that k is a tree functor and d is the list functor, and you were given a ran tree empty list string. If you pass it a function string to a tree int, you get back a list of int, and so on. That's kind of a lot of stuff. So let's map one thing by one here. So we have this functor, which is going to be the tree. We have the
yep,
d functor, is going to be the list, and we have the contents of both of these containers, which is going to be the string.
yep,
Then this function aki is f,
yep.
and if you use this ran thing and you apply this f, you're going to get back a di, which is a list of strings. Oh,
A list
a
of ints
list of
actually.
ints. A list of ints. Uh, the right can extension will use your function to produce a tree and then repackage it into a list. For instance, you may pass it a parse the generated parsing tree from a string, and you get a list that corresponds to the depth first traverse of this tree. I think these examples should be provided because it sounds so cool, but because everyone is fearing what the heck this is, you don't want. I think it would be very good to see these type of examples written in the book or provided as a footnote to a repo. Uh,
Yeah,
the right
those are pretty
extension.
interesting.
Go on.
I was just gonna say there's an example coming up as well, which is like It's from a paper that I read a long time ago, and I should reread it now that I've read this book because I think it will be good.
Yeah, probably better.
Uh, yeah, I'll probably understand it better now.
Yeah.
But let's keep going.
The right can extension can be used to calculate the left adjoint of a given functor by replacing the functor d with the identity functor. I think that's kind of what we did up there with the identity functor in the math.
Yeah, it is. It actually is.
This leads to the left adjoint of a functor k being represented by a set of polymorphic functions of this type. Yeah. Suppose that k is a forgetful functor from a category of monoids. The universal quantifier then goes over all the monoids. Of course, in Haskell we cannot express monodal laws, but the following is a decent approximation of the resulting free functor. I forgot free functors. I remember what is a free monoid, but I don't really remember what is a free functor.
Free functor. Uh, I would have to go back to. I think
Yeah,
this is talked about when they introduced adjunctions.
I think it's before that. Okay, let's not be so pedantic. So we have this type alias here. As expected, generates monoids or Haskell lists. So if you receive a list of A's, you can actually generate this guy using a fold map, which is kind of fun. Uh, oh, I see what's going on. Okay, this fold map has the restriction of the monoid.
Yep.
This F is this,
Yep.
uh, and
And
then
we're using the identity to derive this, so the I and the A become the same type.
yes. So that's why the fold map works. And then we also have a from list, which is basically yeah the same thing. Well, not the same thing, but makes sense
It's the
given the
same
order
thing
one.
but backwards,
Yeah.
basically.
The left can extension is a coend, so this is the same thing that we saw before. So it translates to the extension quantifier symbolically, but of course in Haskell this becomes for all again. In this case we are using GADTs. And the reason is because we are using a type variable that is not being introduced on this side of the thing.
Yep.
The interpretation of this data structure is that it contains a function that takes a container, so ki, of some unspecified i's and produces an a. It also has a container of those i's. Yes, it has this. Since you have no idea what i's are, the only thing you can do with this data structure is to retrieve the containers of i's, repack it into the container defined by the functor k using an natural transformation, and call the function to obtain the a. So basically, you have a container of i's. You need to transform it using natural transformation because both are functors to a k container,
With
and then you
yep.
apply this to get the a values out of it.
Yep.
I have no idea of an example, but let's read.
Well, there's an example in here. For instance, if D is a tree and K is a list, you can serialize the tree and then call the function with the resulting list to obtain an A.
Yeah, but like this is the type of stuff that you would do it yourself, and you will never think that this is a left joint left can extension. You know, the left can extension can be used to calculate the right adjoint of a functor. We've seen this before. We know that the right adjoint of the product functor is the exponential, so let's try to implement it using the can extension. I forgot where we concluded this, but I think we did. Um,
Yeah, we saw it a long time ago.
long
I
time
don't
ago.
remember where either.
This is indeed isomorphic to the function type, as witnessed by the following pair of functions.
uh, yeah, basically it's representing the functor in this case, not the functor, the function type
No, yeah, that part
by
is I got it. It's translating. this representation to the other representation without losing semantics. But I'm trying to figure out how that's being done.
Basically, it's turning a function into a pair where the right element is a unit, but then you are pre-composing the original function with the FST to ignore the unit and just take the left value of the pair.
Mm.
And then the from expression, it's creating a function that takes an A and calls the F that we just established, takes a pair, ignores the right thingy, and
Retrieve the container of X is just trivially is just a trivial identity container and the function F. Repackage the container using the network transformation between the identity functor and the pair functor. Call the function F. Yeah,
yeah,
talking about this. Yeah, I think I see. I just don't get why we need the I. What is this? What is this?
that's the identity functor.
That's not how you do that though in Haskell. There is a thing called identity. Like uh, it's written all over identity. It doesn't have an I thing.
Well, maybe they figured for this book that identity is too long, so they just abbreviated to I.
Maybe during the writing of this version of the book, it was called this. Maybe. I've never
That's
seen it
all.
before.
Hmm.
But yes, okay. So this is identity functor, which, as far as I can tell nowadays, it's just written completely identity with capital I. Um, okay, okay, no, that's okay. And then a free functor. An interesting application is the construction of a free functor. Suppose you have a type constructor, that is, a mapping of objects. Is it possible to define a functor based on this type constructor? So you're having an arbitrary type constructor. We don't even know if it's a functor. But apparently you can use can extensions to automatically create one out of any type constructor.
Yeah, this is the bit. It will even link to the paper that I mentioned actually, but
Can you define a mapping of morphisms that would extend the type constructor to a full-blown endofunctor? The key observation is that a type constructor can be described as a functor whose domain is a discrete category. A discrete category has no morphisms other than the identity morphisms. Given a category C, endofunctors are functors that go from the category to itself, right?
yeah, they are.
Okay. Okay. Given a category C, we can always construct a discrete category mod C by simply discarding all known identity morphisms.
Not mod, this is abs actually.
In my school, they called mod.
But mod what? Modulo takes two parameters.
No, I think you're right. This is abs. This is absolute. I said bullshit. No, I didn't say bullshit. In Portuguese, I think it's called módulo. Yeah, this is a language thing.
I have no idea why that is, but I remember hearing that word in the context of complex numbers, actually.
Yeah, because módulo in Portuguese is used to talk about the magnitude of complex numbers.
Which is weird, but okay.
But let's use absolute because I think this is a 100% Portuguese thing. Absolute by simply discarding all non-identity morphisms. A functor f from ab C to C is then a simple mapping of objects and what we call a type constructor in Haskell. Wait a moment. A functor f from ab C to C is what we call a type constructor in Haskell. I don't quite get why that's the case.
Because a type constructor doesn't map morphisms. If it did, it would be a functor, right?
Ah, we only map objects.
Yeah.
Okay, I see. That example was good. If it was doing mapping of morphisms, that would be a functor.
We would have access to fmap, but in general we don't.
That makes sense. There is also a canonical functor J that injects abc into C. It solves identity on objects and on identity morphisms. The left-hand extension of f along J, if it exists, is then a functor for C to C. Yeah, this is the thing we saw before. It's called a free functor based on f. So what are we doing here? This is a product between f of I, so applying f functor into the I object, because, well, we have the subscript.
Yep.
Then we are saying that this is a home set.
No, this is a pair actually, where we have a morphism from Ji to A and an Fi.
This is a pair.
This is a pair.
We changed the syntax.
No, we didn't. It's just that in this case, the left side of the pair happens to be a morphism, so it's a C parentheses whatever.
I don't follow. To me, you said this is a morphism, you said?
No, no, no. The C parentheses JIA close parentheses, that's a morphism. Well, actually, in this notation, this would more properly be a home set, I guess.
Yeah, that's what I said.
But this is the left-hand side of a pair. You see the X there?
Yeah, this is the left-hand side of a pair. Oh, I see what you're saying. We are overloading the notation that is changing the semantics between this thing.
No, we're not. We're just nesting things normally, I guess. It's just that we don't usually see a pair of a home set and a functor like this. It's just, well,
No, this is
it's
not
a
a
thing.
functor. This is an object, right?
Well, yeah, we're trying to define a free functor, so this is actually an arbitrary.
Yeah. So this is an object.
Yeah, there's a type constructor, which is not really a functor yet.
Yeah.
And the left-hand side is a morphism, a home set of morphisms.
Yeah, but as you said, we don't see, like, what does it mean to have a pair in which the left-hand side is a home set? So that's why you said that this is a single
Well,
morphism.
yeah. A home set is it's basically at the type level. A home set becomes an arrow type essentially.
No, that's okay. But I think your previous observation was it convinced me more that this needs to be a single thing. Because if it was a home set given a notation, what does that mean?
It will be a single thing after you instantiate an object of this type.
Not necessarily, actually. You can have multiple morphisms from this object to A.
No, what I mean is that a construction, if you try to instantiate an object of this type, you have to choose one morphism in the set to use to construct it, basically.
Oh, so it's because of that your understanding that this is a single thing.
Yeah, at the type level, yeah, this can be an arbitrary arrow. But when you actually go to construct a value of this type, you need to choose one, basically.
Okay, so that's why this is not a home set. In Haskell, we will write it as this, which is what you said, right? So there it is. The function. This is the arrow.
Yep.
And this is the f of I. So this is the pair, quote unquote, pair.
This is the pair.
Indeed, for any type constructor f, free f of f is a functor.
And it is a functor because it cheats, basically.
What do you mean?
It doesn't actually apply the function, it just remembers it.
It doesn't actually apply the function, it just remembers it.
Yeah. See, f of I is still f of I after you call fmap, you see?
No, but this is a type constructor.
No, but look at the definition of fmap. It takes morphism G, right?
Yeah.
Then it pattern matches on the fmap on the free functor, right?
Yeah. So this is not this is a type constructor.
No. This is an object which has a type which is f of I for some I.
No, you were right. This is this, right? And this is this thing.
No. This f of I is, you see the for all I there? on the right hand side of the equals.
On the right hand side of the equals, you say you're talking about
Yeah,
this.
yeah. You see, the f of I is the type constructor f applies to this existential variable.
Hmm. Okay, so far.
But in the definition of fmap, we don't actually do anything with it. We just say, okay, I have a morphism G. I have the age that was used to construct this free functor. And the result is just I do G after age and I don't touch the Fi. I'm cheating. I'm not actually applying the function.
Oh, I see. It's because f of I is actually the value that you're holding inside,
Yeah,
and you have a function that does something with that given some I generates the value of that type, and you're receiving a function g. But instead of using the thing that you already have stored in there, you're not doing anything,
you're just remembering it for later, essentially.
and you are basically precomposing the. Yeah. Wait a moment. How does this type check though? Because this is a
Because
function from A to B.
and age is a function from I to A.
Yeah. So you're going. This is an I to B.
Yes, and the result now is a free F, F, and B.
But you have an A there.
No, you don't. You have an F of I there.
What is the type of that?
F of I for all I.
What?
Yeah, the I
Oh,
is
this
encaps.
thing.
Yeah, the I is just private data that you don't show anyone.
Ah, I see. I was really. Oh man, I think I know where the confusion that I made. I was reading this as free f, but this doesn't make sense because free f is the actual. It's the type name. This is the
Yeah,
constructor thing, which means that f of I has this type here, which can be anything because it's for all I. So after all of this, we have a free f of b. Yeah.
which is the type which is the type of the output of G after age in this
What is the
case.
use case of this?
Scroll down a little bit, it has an example actually.
As you can see, the free functor fakes the lifting of a function by recording both the function and its argument. It accumulates the lifted functions by recording their composition. Functor rule is automatically satisfied. This construction was used in a paper Freer Monads, more extensive effects, which I didn't read.
It's a paper from Kislyov, and it's actually part of a series of papers that he wrote, and they lead up to algebraic effects essentially.
Alternatively, we can use the right can extension for the same purpose. So what is the difference?
Instead
Uh,
of being a pair, it's actually a function.
yes. We changed the name for some reason. This is now not fmap, this is free f. And the type constructor happens outside of the for all.
Yes.
It is to check that this is indeed a function, a functor. So you construct a new free f, you receive a new I called bi. You already have this function. You have a function with this type called r, called r. Uh, and what you are doing.
You're
No, wait.
constructing a new
R is
function with.
this thing.
Yeah, it is this entire thing.
This entire thing. Bi is this.
Yes.
And you're receiving a G which is A to B. So you're receiving an A, uh, returning a B, precomposing with this. So this is now actually a Bi here, B to I, which means that we are doing B to I at the wait A to a B. No, this is still an A to an I. This is still an A to an I. And if you are
Yep.
passing that to R, we are getting an f of I after that. Okay. But you also change the I to the A. No, this actually keeps it, right? This actually
You
keeps the A.
can.
It's always A to I here.
Yeah, it
right?
changes the a on the type parameter on the left side of the equals, right? When you call fmap. Well, which is that a actually, but
Yeah, no, that's what I mean. This will always be A because an F map is A to B, but you are removing the B. Is that what am I correct on this? Or am I saying bullshit?
let's see.
G,
This is indeed a functor fmap of g.
G is A to B,
G,
right?
yeah, g is a to b. You
So
take the a,
you take the A, you get a B, you are composing that with BI, which is this.
which is going to be from b to y because this is now the output of the fmap.
So this is a B to I. So the type of BI is B to I. So this entire thing is B to I. A to no A to I.
Yeah,
A to I. And then you pass R, which is something that picks that function and returns an f of I.
yeah.
Um, but do you see that the B was removed in the middle of the equation here? Am I crazy? Because this is an A to the end result of this is an A to I, right?
Well, yes, but now the bi is the parameter that will become the new function
Ah,
of the
okay,
next
that's
instance.
true.
You see?
Okay, so that's why the type changes because the new free f is actually now expecting a B to I.
Yeah.
Fucking damn it. Okay, okay, okay. Anything else? I'm gonna finish the recording.
uh, no, just scroll down a little bit because there's actually a link to that paper here. See, it's from Kislyov, obviously.
Oh, the famous Oleg guy. I see.
Yeah, that guy.
I see. Well, something else to add to my list of reading.
Yeah, Kislyov is amazing. Like,
Yeah, yeah.
he's a.
You already did marketing for him multiple times already.
I like his work.
Okay, cool. Finish the recording now.